Hi everyone, I'm Justin Chan from the University of Washington, and today I'll be talking about an electronic-free approach to smart fabric designs. So as we all know, smart fabric designs today, like Google's Project Jacquard and the LilyPad Arduino microcontroller, have renewed interest in using everyday clothing as a platform for computing and interaction. However, the expressive capabilities of these devices are primarily enabled because of their onboard electronics. And these electronics require batteries, which can be cumbersome to charge. In this talk, we take a contrarian approach and ask the following question. Can we create a smart fabric design without any electronics or batteries? A positive answer would enable a design that can be fabricated using only off-the-shelf embroidery machines. Such an approach would also be battery-free and will eliminate the need for waterproof casings that protect electronics from rainwater and laundry cycles. And in fact, you can enable a variety of applications with this approach. For example, imagine everyday clothes that had the memory to store codes and invisible images without the burden of wires, batteries, and radios. Or imagine interacting with your smartphone while it is in your pocket by gesturing with a glove made only of fabric. So conductive threads are typically used in smart fabric designs either as a wire to carry electricity from one point to another or as a capacitive touch sensor. What we found out was that these off-the-shelf conductive threads also had magnetic properties. And our key insight was to leverage the magnetic properties of conductive thread for interaction and offload digital logic to an external device, like a smartphone. So I'm going to show you just a brief demo of what I mean. Right here, I just have an off-the-shelf roll of conductive thread, which has been magnetized with a permanent magnet. And here's an Arduino that's connected to a microcontroller. So if I just move this thread here, you can see that the magnetometer actually senses the magnetic properties of this roll. And you can even embroider the conductive thread into a regular textile, and you can see that the magnetometer actually detects that. So the cool thing about this is that all smartphones already have magnetometers. So with this capability, existing smartphones can sense the presence or absence of conductive thread. So in this work, we present three key contributions. The first is that despite the growing interest in fabric computing, we're the first to harness the magnetic properties of conductive fabric for interaction. Secondly, we provide a detailed characterization of magnetized thread. And finally, we build electronic-free data storage and gesture recognition applications. I'll first begin with the material characterization of an off-the-shelf conductive thread. There are three key characteristics that we care about when we're analyzing this thread. The first is, does the embroidery style have any effect on the received field strength? Secondly, what is the magnetic field strength decay over distance? And finally, we look at how the magnetic field strength decays over time. So these threads are ferromagnets. They're not permanent magnets, so we can expect that the field strength will actually diminish over time. Okay, so in this experiment, what we did was we embroidered a 2.5 centimeter square patch of magnetized fabric in 9 different styles. And then what we did was we measured the field strength on a smartphone, and as you can see, these are the received field strengths. The key takeaway point is that style actually matters, and that denser styles produce higher field strengths. Next, we ask, how does the field strength decay over distance? To measure this, we embroidered 3 different sized patches, 2.5, 2, and 1.5 centimeters squared, and we measured it over a distance of 20 centimeters. We can see that the field strength does drop off quickly, but it works up to distances of about 1 centimeter. And the point here is that these were done with off-the-shelf threads. This wasn't something that we customized. And if we did create custom threads, this could probably work over longer distances. Finally, we measured the decay in field strength for these 3 patches over a week. After 1 week, we remagnetized the patch. As you can see, the patches lost between 28 to 36% of their field strength over a week, And when we remagnetize the patches, they regain their original field strength. So we note here that none of our patches got completely demagnetized. And in fact, all of our patches, even the ones here today that have been sitting around for several months, they still retain some magnetic field strength. Building on these observations, we show 3 key capabilities. The first is a data storage scheme where we can tag everyday clothing with information. Secondly, we show an imaging scheme where we can embed invisible images onto fabric and image them back in one shot. And finally, we show a gesture recognition scheme where we can interact with a smartphone in our pockets using just a glove made out of fabric. So let's begin with data storage. First, we ask ourselves this question. If we wanted to tag everyday clothing with a unique identifier, how do we do this? The prevailing approach today is to use RFID tags. But the problem is that RFID tags require RFID readers, which are extremely expensive and can cost hundreds to thousands of dollars. Additionally, RFID tags cannot be read on smartphones. What we desire is an unobtrusive tagging approach that can, in fact, be read on smartphones. So our solution is to magnetically encode bits onto conductive fabric in a way that bits are encoded onto a magnetic hard disk. So to achieve this, we embroider a thin 5mm strip of magnetized thread, and we divide this up into 2-centimeter long cells, which we interspersed with 1-centimeter long guard bands. And the guard bands are there to prevent interference between adjacent cells. And we note that these tags only cost about 17 cents, which is very competitive with the price of RFID tags. So we simply magnetize each cell with a north and south magnetic pole to encode 0 or 1, and then we can just swipe it across a smartphone's magnetometer. As we can see, when the smartphone encounters a pole, you see a minimum, and when it encounters the opposite pole, you encounter a maximum. And you can see this in action in this short video here, that the readings on the XYZ axes change as the user swipes the strip. We can just combine the readings on all these 3 axes and then decode the bits. All right, so one important question you might ask is, okay, how durable are these tags to washing, drying, and ironing? What we did was we encoded a set of bits onto a tag, and then we exposed this strip to hand washing, machine washing, drying, and ironing at 160 degrees Celsius. And we did not remagnetize the bits between the processes. What we found out was that after all these processes, we were in fact able to decode the bits perfectly. And this here just shows the average change in the magnetic signal after each of these processes. And as you can see, there's actually very little decrease in field strength, even in the presence of water and heat. So next, we ask, how programmable are our tags? To test this, we magnetize a single strip with a code, and then we read it with a smartphone. And then we repeat this with 9 different tags for a total of 10 different codes. As it turns out, in this figure, we were able to decode the bits perfectly each time. And in this figure, what we can see is that for each new tag, that's the average magnetic field strength. And the key point here is that there is no noticeable degradation in field strength no matter how many different codes you apply to each tag. And all these changes that you can see here are in fact natural measurement variances. So finally, we show that we can create fashion accessories like neckties, belts, necklaces, and wristbands that are made entirely out of conductive fabric. And these accessories can be used to store data that uniquely identifies clothing brand or name. So beyond simple identifiers for clothing, we now ask, can we embed invisible 2D images into fabric? So to that end, what we envision is we can use these magnetized fabrics as a canvas that users can use to draw invisible images on. And they can do this with a 3D printed pen with a permanent magnet attached to its end. So they can easily encode bits by manipulating the polarity of each cell. And to decode the bits, we can hover a 3x3 array of magnetometers over the fabric and read the data. So you might be asking yourself, how small can each pixel be? To test this, we took a 9x9 centimeter square piece of fabric and embroidered and encoded a checkerboard pattern at increasingly higher resolutions. We then measured the magnetic field strength of each cell, and as you can see, it is possible to resolve the pixel size up to a size of 1.8 centimeters squared. Next, we test the expressivity of this platform. And what we did was we encoded the letters A through Z and the numbers 0 through 9. And as you can see, it's possible to image all of these characters. So with this design, you can embed 2 to the 25 or more than 3 million possible images, which is sufficient for many tagging or authentication applications. So we show here that users can authenticate themselves using a magnetic patch. So we imagine that such a patch can be an alternative to RFID keycards and be embedded on the uniforms of hotel or mall employees. And these employees can simply scan their uniforms against a door and gain access to authorized areas. Next, we consider the problem of interacting with our smartphones while they're in our pockets. How can we do this with off-the-shelf smartphones without instrumenting them in any way? Additionally, can we interact with tiny, low-power IoT devices without making any physical contact? As it turns out, magnetometers are a great fit for both these applications, as they consume as little power as 72 watts, which in comparison is 1,000 times less power hungry than Bluetooth Low Energy, and they can retail for as low as 80 cents. So how do we interact with these magnetometers? To do that, we embroidered a small patch of conductive thread onto the fingertips of a glove. And a user wearing these gloves can simply make these gestures in front of a smartphone's magnetometer, which can recognize the gestures. Of course, there are multiple form factors to this, and you can imagine that the conductive patch is simply, embroidered into the cuff of a shirt here, and I can just wave my cuff in front of my pocket and interact with a smartphone. Here we show a set of 6 gestures that we were able to encode, we were able to detect on our smartphone. A user can swipe up, down, left, and right, or click on the top or the bottom of their smartphone. And these gestures result in distinct changes in the X, Y, and Z axes of the magnetometer. To decode this, we simply detect the peak locations of the axes relative to each other and map them to a single gesture. The key thing about our technique here is that it's a very simple procedure and it does not require any training or expensive processing, which is ideal for a power or storage constrained IoT device. We then built a real-time classifier, as you can see here, that is able to classify between these 6 gestures. To evaluate our system, we conducted a user study with 7 different users who were asked to repeat each gesture 20 times. And our real-time classifier recorded an overall accuracy of 90.1% across all 6 gestures. So with this system, we can easily interact with our smart devices while they're in our pocket. So for example, so you can pause or play your music without constantly having to take your phone out of your pocket all the time. So now we describe some future work. With custom designed textiles and a much more precise magnetic reader, we will be able to generate stronger fields and increase the range of our gesture recognition system. We'd be able to increase the bit density of our tag and store more information. And finally, we'd be able to increase the lifespan of each bit so they don't decay as quickly over time. In conclusion, we harness the magnetic properties of conductive fabric for interaction. We provide a detailed characterization of magnetized thread. And we build electronic-free data storage and gesture recognition applications. That is the end of my talk. Thank you for your attention, and now I welcome any questions.
So, quite interesting talk. I had a question relating to the your 2D matrix. Is it one big sort of patch that's embroidered, or does it need to be embroidered in sort of sections?
It is a single patch. We do not need to delineate or do anything with the patch. It's just a single uniform patch.
And if it was more densely embroidered, could it be smaller even?
We would probably require some custom designed textiles, and we would need a much more precise magnetic reader, because with these magnetic readers, it kind of measures over a large range. So, like a magnetic disk, you would need a very precise reader and writer for that application.
Thank you. Okay.
Hey, my name's Soyoung, and I'm from IM+. This is really fantastic. I know that you're pretty early on in this, but I was wondering if you've done any tests about just it becoming demagnetized through just interacting with the world, or, like famously with B drives, they used to tell you to move your filing cabinets around every couple months.
So the question was about, do these tags get demagnetized?
Yeah, just from like
Yes.
normal.
So in the previous graph, we showed that it decreases in magnetic strength over time, but they do not get completely demagnetized. So for example, this thread here, the last time I magnetized it was like several months ago, but you can see that it still has a really strong magnetic field strength.
I had the same question, but I'll just follow up. So if you have, rare earth magnets that are snaps on your clothing or other things like that, what is have you looked at the BH curve of this magnetic material to see how much you need to change the domains?
So we didn't do a hysteresis test, or rather a lab test for these magnetic threads, but you can see that, they're still very strong. And, in the presence of, say, if you had a permanent magnet on your cuff or whatever, then yeah, I suppose if you're doing gesture recognition, yes, it would affect the smartphone's ability, because the dominant signal would be the permanent magnet and not this magnet here. But we think that's a very rare case, and most of the time, you're not going to have a permanent magnet close by to your phone. You would just be having the thread, and that magnetic thread will be the dominant magnetic signal, which we be able to detect every time.
Great.